is a log-based transactional memory. So it's from HPCA 2006, so it's a few years after the first idea of transactional memory. The objective of this presentation is to learn how LogTM differs from a bunch of other transactional memory models that is presented from the paper just presented by Ali and up until now. We'll also learn about eager version management and eager conflict management, which is the key part of this LogTM. So not going to get into this too much because we already discussed in the previous presentation, but essentially it's a way to kind of like package a bunch of memory instructions into a group in a sense. And it's either they all commit or nothing commits, and that's the entomosity property of it. And the other property, as we discussed, is that it's isolated from other transactions, so that transactions cannot see the partial state of another. And to achieve these two properties, the LogTM, or transaction memory in general, requires a version management and a conflict detection. So version management is a way to say, how do we keep the data up to date, or how do we revert back to a different data? So upon finishing a transaction, it can either commit or abort. And during the transaction, some memory data would change. So upon commits, then the new data must be made visible, and upon aborts, old data must be made visible. And there's only one place to put this, and that is where it should be, which is the address where data should be. But then if you have multiple versions of it, then the question is, where do you put it? So the lazy version management is kind of commit centric in a sense that you place the new data in a separate structure. For example, some older transactional memory proposals would put it inside a speculative cache or something. And once, when you commit, when you actually need it, then that's then brought into place or copied to where it should be. Whereas eager version management is that you would always put it in the right place, and then you'll have to revert it using some other mechanism. For conflict detection, we need conflict detection because it occurs when transaction is writing to a set of data, and another transaction would like to either read from an outdated data or write to the same location. So lazy detection operates when when a transaction tries to commit, rather than eager detection where it tries to detect immediately when the load and stores instructions they execute. So using these two things, we can kind of make a political compass of sort, except with eager and lazy version management and conflict handling. There is this transactional memory coherence and consistency, or TCC, that they described, and it's both lazy in terms of version management as well as detection, as in new data is kept in the speculative cache until commit, and detection is only verified during commit. Then we have a large transactional memory, which does have eager conflict detection. But upon conflict, the LTM, according to the paper, but because I haven't really read LTM, is that it would try to walk the uncacheable in-memory hash table, which is where they store the some of the tracking, I think, data for for the transaction. And then there's the virtual TM, which is pretty much the same, except it has a per address space virtual mode that allows it to handle cache evictions, paging, and context switches. And then we have the unbounded TM, which is both eager conflict handling and also eager version management. But according to this paper, they say that the unbounded TM is a little bit too complex, and somehow authors abandoned the idea. And then there's the LogTM. So what I found helpful for me is that I use this Git analogy. I'm sure most of you have worked with version tracking and group work in some sense. So we have this code base, and we need to have multiple people working on the same project repository. And now it's not uncommon that multiple people will try to make changes to the same files. So we need some kind of version tracking so that we can have a diff log or some sort. These developers, they will stage their changes where Git keeps a diff compared to the head being the up-to-date version. So developer A, for example, can commit their changes once they're ready, and the new file becomes the new head. That is kind of analogous to how transactional memory kind of commits their transactions. In some cases, developer B will commit the changes, and because it's the same file, they will have to resolve some conflict. So that's the analogy to the conflict resolution part of transactional memory. All right, to do version management, we need to make some changes to the core, at least in terms of LogTM. Is that okay? So we're gonna have the most up-to-date value in place, so that therefore we need some kind of structure to track the changes, right? So let's place it in a log. And the log requires two registers, and one is the start, which is the base address of the log, and the base pointer, which points to the top of the stack, because the log is kind of a stack in this case. So let's add that. Furthermore, let's add a TM count register to indicate whether a transaction is occurring. So if it's a 0, then that means no transaction is occurring. And if we increment it, that means there's some, and decrement it when one's finished. So it's also kind of like a stack, except it's just a number. Lastly, let's add a checkpoint shadow register when transition transaction mode. They only briefly talked about this, but I'll just mention it here. Okay, so now let's think about the changes we have to make to the cache. So they propose adding a R and W flag for each of the cache block, where W flag is avoiding redundant writes and R flag is used for handling conflicts. Okay, so in terms of transaction stores, during transaction, as we talked about, when we're storing new data value, we're storing in place. That means the new data sits where it's supposed to, corresponding to the actual address. And at the same time, we write the old values to a log. But we can buffer this log since the log isn't needed until abort time, which is sometime in the future, but not immediate. So what does this give us? This gives us really fast commits, because once we finish, there's no need to copy. And then it's like git commit. And then all we have to do, some of the house cleaning stuff that we have to do, is just to reset the lock pointers. And we don't even need to override the data. So that's just resetting the registers, and also flash the read and write bits set to 0. And now abort requires restoring the data, which takes a little bit more time. Okay, so that's a lot of rules and how this behaves. So let's do an example. So here we have an example that is kind of copied from the paper, but we can follow along step by step. So consider a virtual address space, and we assume 64 byte blocks. And we have 12, 23, and 34 in these areas. But so, and also let's consider the log base and log pointer, the TM count register. So now let's say we execute begin transaction. So now we're starting a transaction, TM count increments to 1. And now let's execute an instruction that loads the address 0 to R1. So we have R1 that copies the value in there, and because it's a transactional load, we set the R bit to 1. Then we increment this value, for example, that becomes 13, and say we want to write it back to the same address, in which case, I mean, it's kind of spoiler because you already read the paper, so what would be the new address? Because we're doing a transactional store, so that means we need to make a copy of this data inside the log, so the log pointer has to increase. And in fact, we copy that in there, and the new log pointer is 1048. And the reason that's 1048, we'll get into a minute, but essentially this has the value of R1 has been written back into the data block. And the reason that it's 48 is because we also account for the address, which is in bold here. Okay, so now let's commit the instruction, sorry, the transaction. So to commit, we don't need to do anything with the data because, it's written in place. 13 is already there. Or, sorry, not 13, 13 because it's in hexadecimals. And all we need to do is to decrement the TM count and reset the log pointer. And we don't even need to reset this because it will get overwritten. Okay, let's rewind though. Let's go back. So what happens if we don't commit and we abort? So we'll have to traverse the log as a stack and then revert by putting these data back to its original address, like that. And then, again, decrement and reset the pointers. So abort takes time, right? Because we have to traverse the log. But luckily it's rare because as they show in their experiments is that log is actually making a small is a very small fraction of the execution. So let's assume commit as a default case and let's optimize for that. So that's what they said. Another part is conflict detection. So as talked about before, we have the R and W bits, and these corresponds to these modify owner exclusive and shared coherence status. So the coherence protocol is extended to allow eager conflict detection. That kind of boils down to 5 steps. So when there's a coherency request, the requesting core requests a directory for the coherency. The directory forwards that request to all of the shared cores, and then the responding core observes its local state or the R and W bits, and the responding core also responds to the requesting core either a ACK or NACK. It's either no conflict or conflict, respectively. And following that, the requesting core lets the directory know whether they succeeded. So just a review of the directory coherency. Essentially, we have these processors that's in different, that communicates with the directory, which has a share list and also the state. So let's jump into an example based on the steps that we talked about. So let's say P0 starts transaction, TM count now is 1, and it calls a GETX request to load address 10 into R1. Okay, so let's load it to R1. So the directory provides the data to P0, and now P0 has now the state of M because it's a GETX. So both R and W bits are set to 1. And now P0 makes some modifications and changes this to a AF. Okay, now let's consider P1 starts an transaction. So now that's a TM equals to 1. And it requests for the same address. So it says, hey, can I have the block for address 0? So it talks to the directory. The directory says P0 owns it. So it forwards the request to P0. P0 checks its own R and W bits and says, no, I'm still using it. So it sends a NACK signal to P1, and P1's like, okay, you know what, fine. I'm going to say NACK to the directory because I haven't made any changes. There are cases where caches overflow, and in which case, if a transaction has a lot of writes, it can overflow the cache, right? So each processor now has a overflow bit to indicate whether an overflow occurred. And even if it occurs, we continue to let the directory forward the request even when it's blocked. But how do we keep track of the states? Well, we add a sticky state to the directory, so that even when the cache block is replaced inside the owner core, for example, or the core that has the modified status, when other requests come in, we still have we can still maintain the properties of transactional memory. And lastly, to clean up the sticky state, the reason that it's sticky is because we have this lazy cleanup, which is optimized if overflow doesn't happen very often. So let's go back to the same example now with cache overflow. So previously, P0 is in the middle of a transaction. P1 tried to, but failed, tried to obtain a shared block. So now somehow P0 replaces this cache. So it calls a put X or put exclusive, and it's like, hey, can I write back exclusively? And it says okay. And so now it writes back the data to the directory, and now the directory has the updated data, except the DM is now DM sticky, or I use the sushi because it reminded me of sticky rice. But now notice that P0 no longer has the copy of the data. Okay, so now can P1 send a GETS request, right? Well, it says, okay, can I have it now? So it goes look to the table and says, okay, P0 is still on the sharing list. So it goes to P0 and forwards the GETS request. But notice that there is a overflow flag that is turned on P0. So P0 is like, okay, because of the overflow flag, I'm gonna assume there's a conflict. So I say, okay, nah, I still need it, right? So P1, observes the same thing. Okay, now sometime later, P0 commits. What should be the state of in the directory? According to the protocol, it should be the same because it's sticky, right? That's the it's like that's the point of the sticky state. So P0 decrements its TM counter, lowers its overflow flag because it's done, and now this is where we're at. So okay, so P1 asks for the very last time. It says, can I finally have that block? And it says, okay, P0 is still on my sharing list, so I'm going to ask P0. And P0 responds with, looks like I already committed, right? So I'm going to call the clean request. So the janitor comes in and scratches the stickiness off of the directory. And now the directory knows, okay, so P1 is requesting for it, P0 no longer needs it. I'm going to set the state to exclusive and pass the data back to P1. So that's how it handles the conflict. And yeah. So all in all, conflict resolution is that to resolve a conflict, the core either needs to stall or abort. And in the earlier example, P1 could choose to abort, but as we've seen in the example, it chose to kind of reissue the request at some later time. And there are cases where transmissions or transactions could be killing each other due to, as we talked about earlier, either deadlocks or live locks. So we can we can broadcast a timestamp to them, and we add this flag called possible cycle to kind of break the lock. So if one of the earlier transaction already has a lock on it, and if an earlier transaction is trying to request, then we set the lock, and if the lock is set and yet we're still getting a NAC request from an earlier transaction, then we raise a conflict. Some of the software interfaces that described in the paper mostly concerns of these three sets of interfaces where you can program, where you can use their user APIs to talk with this architecture, but I'm not going to go into too much detail. Okay, so how does it do? So what they observed is that there's a speed up across all selected benchmarks for versus like the comparing to using locks. So I found that pretty interesting because they compared it with using locks versus the other aforementioned transactional memory proposals. What they say is that this enables critical section parallelism, which means for the critical sections of the program, you can have more concurrent threads running simultaneously. In this case, the best performing one, which is Raytrace, had an average 3.2 to 5.5 concurrent threads running, which is an increase, according to them. And secondly, a second insight is that, okay, since commits is the typical case, let's maximize the rate of commits. Let's reduce the number of aborts because, aborts will take time, right? And also discards the work. So it's wasted work. So the alternative option is to stall. Well, stall is still bad, but it's better than abort according to them. So they did a experimentation to show that most stalls still had, in terms of number of cycles they stalled, is still fewer than context switch. So wondering if context switching is worth it, but not discussed in depth. False sharing occurs when you think the two cores are sharing the same data, but not really. They're just sharing the same block. So this is bad because it it's not a real sharing, but it still invokes conflicts and increases the chance of stalls and aborts. Number 4, read before log. So LogTM requires a read of the data before we can write and log to it. Now that is extra work if we don't read, but as seen on the right, this column is that in most cases, in a transaction, the read blocks are eventually written into or modified. That should be 5, but they also found is that we can use the buffer to ease the cache bandwidth, because as we modify the log is cacheable because it's in virtual address. It increases the bandwidth. So, we can ease that bandwidth a little bit by using a buffer, and they found that using a buffer of less than 4, to be pretty good for most cases. Okay, but I'm done. Yeah.